Okay, number 2, part A, we're asked to prove that this function is differentiable at this point. So one way to prove differentiability is to use the long drawn out definition as a number 1, but we don't have the time to do that. We're going to use a mathematical power tool, and those of course are theorems. And the theorem says this: if fx and fy are continuous in an open disk centered at the point x naught, y naught, then f is differentiable at the point x naught, y naught. Okay, so if the first partials are continuous in an open disk centered at the point we care about, then the function is differentiable there. All right, so let's go through and find these first partials and see where they're continuous. So take the partial derivative with respect to x. Remember, we treat y as a constant, so it just goes along for the ride. I can just pull out 1 over y as if it were x over 3 or x over 5 times the derivative with respect to x. Of course, that's 1, so I get 1 over y. Fy of xy. Now I'm taking the derivative with respect to y of x over y. And once again, we treat x here as the constant, so I pull him out front. I take the derivative of 1 over y with respect to y. So I'm going to get negative x then over y squared. So those are our first partials. Now, they're not continuous everywhere. They have a big problem at y equals 0. So they're discontinuous along y equals 0, which is the x-axis. So let's check out the point we're looking at. Here's the y-axis. Everything's fine on the y-axis. I'm going to draw the x-axis in red because that's the forbidden zone. Now, where's the point we care about? Well, it's at 1, comma 2, which is up here. Can you find an open disk centered at that point that doesn't hit the x-axis? Well, sure. There's lots of them. I've crudely sketched one of them there. So, since the first partials are continuous on this open disk, I can conclude the function is differentiable at the point 1, comma 2. All right, so the theorem hypotheses are satisfied, so I get the conclusion. And that'll do it for 2a. Part B, we're asked to use differentials to approximate this quotient. Now, since it's part B of number 2, we expect the function we had in part A to get involved. But if you didn't have that part A, how would you know what function to use here? Well, let's say I asked you to approximate this. Well, what would you do? You would take 1.2, that's roughly 1. 1.9, that's roughly 2. You would approximate this by 1/2. Every number that you changed becomes a variable. Okay, since 1.2 and 1.9 are different, when I rounded them, I'm rounding 2 different variables. So that would lead you to consider the function fxy equals x over y. And what are we rounding them to? Well, I'm rounding it so that the x is 1, the thing on top is 1, and the y is 2. So we're looking at f of 1 comma 2, which is 0.5. So if you look back at part A, in part A we were looking at the function f of xy equals x over y. And what did we do in part A? We showed this was differentiable at the point 1 comma 2. Since it's differentiable at the point 1 comma 2, we can use differentials then to approximate the function value at this new point. So that's what we're going to do. We're going to approximate this, which would be what? Well, the top number is what I'm calling x. That's 1.2. The bottom number is what I'm calling y. That's 1.9. Approximate that using f of 1, 2. Okay, so it all depends how pedantic you want to be with this. We know that our x naught then is 1. That's the x value we're starting with. The y naught is 2. The delta x is going to be the new x minus the x we start with. So that's 0.2. The delta y is the new y minus the y we start with. That's negative 0.1. So what I'm going to do is get the differential df. That's fx at the point I know about, delta x, plus fy at the point I know about, delta y. Now from part A, we already know the partial derivative with respect to x is 1 over y, and we know the partial derivative with respect to y is negative x over y squared. So I can go ahead and plug the numbers in. F of 1, 2 is 1/2, and fx at 1, 2 is 1/2, fy at 1, 2 is negative 1/4. So I put that in here, and I get 1/2 times delta x, which is 0.2, plus negative 1/4 times delta y, which is negative 0.1. And we can convert all this to decimals, or however you want to do it. Convert it to fractions. 0.2 is 2/10, so 2/10 times 1/2 is going to give me 1/10. This is going to be 1/10, so that's 1/40. You get a common denominator. What do you get? You get 4/40 plus 1, so you get 5/40, which is 1/8. Oops, not 1/18. It's 1/8, which is 0.125. And then it all comes down to this. All right. Since f is differentiable, I'm going to use the actual change in f is approximated by the differential. Okay, so the actual change in f would be f of 1.2 comma 1.9 minus f of 1, 2. And the df we computed was 1/8, 0.125. So f of 1.2 comma 1.9 minus f of 1, 2 is approximately 0.125, which means f of 1.2 comma 1.9 is approximately equal to f of 1, 2 plus 0.125, and f of 1, 2, that was 1/2, 0.5. This is 0.625. So when it's all said and done, 1.2 over 1.9 is roughly equal to 0.625. Now if you go off to your calculator and get the actual retail value of 1.2 divided by 1.9, it's 0.632-ish. And so you can see the approximation really isn't that bad. So that'll do it for 2B, and that'll do it then for quiz 7.